Swayam Prabha. Digital India. Educated India.
Welcome back to the fourth lecture of the fourth week on bioenergetics of life processes. So, the last lecture when we concluded, we talked about how the manganese cluster works and the charge accumulator model, where 4 protons are being generated and 4 electrons are being ejected out, while at the cost of 2 water molecules, where the 2 water molecules get entrapped into the manganese cluster, where 4, as of now what we know, 4 to 6 manganese atoms are clustered in a way and sitting at different oxidation state, which can unzip the water molecule and eject out 4 protons and 4 electrons, and as a byproduct a strong oxidant, which is water. Now, the story, if we go back, so we talked about this strong reductant, okay. So, which eventually leads to the formation of the dark reaction, which we are not dealing here, which is the Calvin cycle, where the carbohydrate synthesis happens. But end of the day, what is most important from the bioenergetics perspective for you to understand is that you needed a perennial electron source, and in this case, since water is the perennial electron source, we are not only generating as a byproduct oxygen, this process also leads to generation of lot of protons, and that leads to a proton gradient. So, whenever we talk about a gradient, we talk about it could be either a pH gradient. So, whenever we talk about a proton gradient, that essentially means H plus ion concentration is higher. So, when you talk about a higher H plus ion concentration, the first thing which strikes you is the pH gradient, which is pH is what? Essentially H plus ion concentration, right. So, we have a neutral pH where H plus OH minus is at equilibrium. Then if the H plus increases, then we are the lower pH from 7, 6, 5, 4, 3, 2, 1, 0, your H plus ion concentration goes on rising, whereas if you go on the other direction from 7, 8, 9, 10, OH minus ion concentration increases. Okay. So, any form of gradient for any kind of energetics, you have to realize, you always remember this, you have to have a gradient, some form of a gradient. That gradient could be created by any form of ions. It could be H plus ions, or something, or an electron gradient or a proton gradient, but you have to have a gradient, or you could have an ionic gradient. So, you can have gradients like you could have a gradient of ions, some positively charged ions on one side, negatively charged ion on other side, or higher concentration of positively charged. Say for example, if you think of the cell, when we write a cell. So, this is lecture 19, which is the 4th lecture of today. So, this is week 4, lecture 4, W4, L4. Okay. So, when we see a cell, say for example, this is a biological cell with a nucleus and everything. So, you have sodium, which is higher outside and sodium lower inside. So, essentially if I have an equivalent circuit model for sodium, it will be something like this. So, there is a sodium gradient. In other words, this is, you can call it as an ionic gradient. Okay. So, say for example, similarly this ionic gradient could be utilized to generate a force. Okay. Similarly, if we have, say just for a hypothetical situation, if I have something like this, where I have a lot of protons higher on the inside as compared to protons outside. So, what will happen? There will be a proton gradient, something like this. Okay, there will be, and such gradients could be utilized to generate energy, because as we know by the basic thumb rule, from the higher potential things flows towards the lower potential, and during that process many useful work can be accomplished. It is just like, say for example, water is falling from higher altitude to lower altitude, you can utilize to produce hydro energy, okay, by hydroelectricity. Exactly by the same way, as long as you can create a gradient of anything, you can always do some useful work. And today we will be talking about a fundamental concept which was first proposed by a gentleman called Peter Mitchell. Peter Mitchell is known in history for one of the boldest hypotheses called chemiosmotic hypothesis. In the next class we will talk a little bit more about chemiosmotic hypothesis of Peter Mitchell, but today we will talk about this basic concept that ATP synthesis is driven by a proton gradient, okay, across, now this part is important, across thylakoid membrane. So, in 1966, there is a gentleman called Andre Jagendorf showed that chloroplasts synthesize ATP in the dark when an artificial pH gradient is imposed across the thylakoid membrane. So, you remember the thylakoid membrane? I told you the photosystems are lies there, and if you could impose a pH gradient across it, say for example, somewhere or other you create some kind of a, across this membrane you have a pH gradient, then this could lead to ATP synthesis. To create this transient pH gradient, chloroplasts first were soaked in a buffer of pH 4 for several hours. So, you take isolated chloroplast and soak them in a buffer of pH 4. Okay. So, something like this, you take a thylakoid membrane, and pH 7, pH 4. Okay. So, to create a transient pH gradient, chloroplasts were first soaked in a pH 4 buffer for several hours. These chloroplasts were then rapidly mixed with a pH 8 buffer containing ADP and PI. Okay. Then what you do, thylakoid membrane, you are keeping them at 4, that you incubate them, and then you incubation for several hours, and then what you do, rapid change of external pH and addition of okay. So, to create the transient pH gradient, chloroplasts were first soaked in a pH 4 buffer for several hours. These chloroplasts were then rapidly mixed with a pH 8 buffer containing ADP and PI. Okay. So, this is what you do, pH 4, pH 4. Okay. Now, followed by this, there is a rapid change of external pH and addition of ADP and PI, which is the ingredient to make ATP. Okay. Then what you observed here is that here you have the pH 4, H plus ions, they move out, and what they do is outside ADP plus PI making ATP, and outside the pH is 8. So what you are observing out here, H plus ion concentration is extremely higher as compared to outside where H plus concentration is lower. So essentially, if I had to put a signature here, it will be something like this. So here you have a pH gradient, like a pH battery. Okay, so the pH of the stroma suddenly increased to 8, whereas the pH of the thylakoid space remained at 4. So it remained at 4, and here you are increasing it to pH 8, whereas the pH of the thylakoid space remained at 4. A burst of ATP synthesis then accompanied the disappearance of pH gradient across the thylakoid membrane. This incisive experiment was one of the first to unequivocally support Peter Mitchell's hypothesis that ATP synthesis is driven by what we call as proton motive force. So there is a proton motive force generated because of the pH gradient. Okay. So now proton motive force. So this proton motive force, which is generated because of the pH gradient, is being supported here. The ATP synthase of chloroplast closely resembles. So there is an enzyme which is involved in it, membrane ATP synthase, which is a membrane bound organelle, which is something like a mechanism of ATP synthesis in chloroplast is very similar to that of the mitochondria, which will come in the next class. The ATP formation is driven by a proton motive force in both photophosphorylation, which is happening in chloroplast, and oxidative phosphorylation, which is happening in mitochondria. Furthermore, the enzyme assembly catalyzing ATP formation in chloroplast is very similar to that of mitochondria and bacteria. The ATP synthase of chloroplast is also called CF1 CF0 complex, and this complex, where C stands for chloroplast and F stands for the factor, chloroplast factor. They are, again, these are all those, if you remember thylakoid membrane, I told you photosystem 1, photosystem 2, they are all sitting there. Okay? So if you just for your recollection, one second, let me, yes. So out here, those are all sitting, and this is the space what I was talking about, the inside and the outside, the stroma, which is the outside space. Okay, so this is where pH 8 and this is where inside pH 4. So you are creating a gradient between inside and outside, and that is the gradient I was trying to show you in this picture out here. That is the kind of gradient you are creating here. So closely resemble and similar, what you see here C, as the next class we will move on to mitochondria, you will see F1 F0, which is essentially nothing but for mitochondria for oxidative phosphorylation. So CF0 consists of 4 subunits which conducts proton across thylakoid membrane, and CF1, like F1, which is the counterpart for mitochondria, catalyzes the formation of ATP from ADP and PI. Okay, so the way this protein is arranged is, if this is the membrane of the thylakoid, so this is how this protein is arranged in multiple loop, something like this. Okay, and this part is CF1 and this is CF0. Okay, and this is the thylakoid space, and this is the stroma, which is outside the thylakoid space. And as I mentioned that ATP, the knobs of the external surface, so these are the knobs of the external surface of thylakoid membrane, are CF1 unit of ATP synthase. And CF1 has subunit composition. There are multiple subunits which are alpha, gamma, beta, which you do not need to really bother. Okay. The electron transfer through asymmetrically oriented. So this is an asymmetric orientation of this particular ATP synthase oriented photosystem 1 and 2, and the cytochrome BF complex produces a large proton gradient across the thylakoid membrane. The thylakoid space between markedly acidic, so this part inside. So, if you look at the thylakoid space, this part is acidic, which is essentially a lot more proton concentration inside, and with a pH approaching around 4. So, pH is around 4 as the Jagendorf experiment, and the light induced transmembrane proton gradient is about 3.5 unit. So, because of the light, the pH gradient is around 3.5 unit. Okay. Light induced proton gradient, when the light is falling, this is, and the proton gradient is created, it is called light induced proton gradient is about pH 3.5 units. Okay. And if you look at it, the proton motive force, or delta P, which is the proton motive force, consists of a pH gradient contribution and membrane potential contribution, which is MP, which is membrane potential. These two sum up to the proton motive force. In chloroplast, nearly all delta P proton motive force arise from the pH gradient. It's purely a pH gradient which is created. On the contrary, as we will read about mitochondria, we will observe the contribution from membrane potential is larger. So, you have to realize this delta P, which is the proton motive gradient, proton motive force, is generated purely on pH gradient in chloroplast. Okay. And about 3 proton flows through this CF0 CF1 complex. Okay. 3 protons flows through the CF1 and CF0 complex per ATP synthesis for 1 ATP molecule. Okay. Interestingly, ATP and NADPH, the products of the light reaction of photosynthesis, are appropriately positioned for the subsequent dark reaction in which CO2 is converted into carbohydrate. And CF1 is on the stromal surface of the thylakoid membrane, and so the newly synthesized ATP is released into the stromal space. So, the ATP which is now synthesized comes out into the stroma. Okay. So, if I have to put it in perspective of how all these 3 reactions looks like, it will be something like this. Now, I will draw the thylakoid membrane. Okay. Now, here is, say for example, this is the thylakoid space what we are talking about. Okay. Okay. Now, on this we have PS1 sitting out here, sorry, PS2. Okay. So, PS2 receives the light. Okay. And what PS2 is doing, 2H2O plus oxygen, which is going out into the air, and plus 4H plus in the thylakoid space. Okay. Now, this electron is traveling through QH2, referred to the previous lecture Q, and it is coming to cytochrome BF complex, CYT BF complex, if you remember. And there also I told you that there is a proton gradient which is being created. There is a proton gradient created here. There is a proton gradient created out here. Okay. Then here through plastocyanin and everything, the electron moves to photosystem 1, PS1. At the PS1 also there is a proton gradient which is created. So, if you look inside, there is lot of, and of course, this is the one which is creating the NADPH, which is taking part in the dark reaction for CO2 to CH2O, okay, the reduction reaction, the major reductant. Okay. And here is the major oxidant which is going away as the gas coming out. Okay. So, now you see there are 3 sources of proton gradient here, here and here. So, inside the thylakoid membrane, if you look at it, inside the thylakoid lumen, your thylakoid lumen you have very high concentration of H plus. So, essentially if I had to put a pH gradient, it will be something like this. As a contrary, outside it is much more less. Now, which is the stromal side, okay? Stroma. Now, here sits that wonderful ATP synthase. Here is the knob outside, which drawing I did. If you remember the drawing which I shown you earlier, out like this, there is a knob like structure outside. So, this is that knob like structure which is facing the stromal side. Here also is exactly the same. Here is the knob like structure facing. So, this one is the one where all the H plus ions are being funneled. The protons are funneled through this, and at this ATP synthesis what happens, and now you correlate it with the Jagendorf experiment. Outside on the stromal surface you have lot of ADP and PI, and because of the proton gradient it leads to the formation of ATP out here and proton comes out. So, this is essentially the vectorial arrangement of photosystem 1 and 2 and a cytochrome BF complex and ATP synthase in the thylakoid membrane. Light induced proton pumping makes the inner space acidic, and the flow of protons through CF0 to the stromal site led to the synthesis of ATP by CF1, and NADPH is also formed on the stromal side. So, all the byproducts are coming on the stromal side. So, this is that most fundamental reaction, a pH gradient. So, remember one more thing, a pH gradient of 3.5 unit across the thylakoid membrane corresponds to a proton motive force of, if the pH gradient is delta difference is 3.5 unit, the corresponding proton motive force delta P what we talk about is 0.2 volt, and the delta G for such situation is minus 4.8 kilocalorie per mole, which is a spontaneous reaction to happen. About 3 proton flows from CF1 to CF0 complex per ATP synthesis, which corresponds to free energy input of 14.4 kilocalorie per mole, okay, of ATP. No ATP, here is the important part, a take home message. No ATP is synthesized if pH gradient is less than 2 unit. So, your most optimal is 3.5 units. But if it is less than 2, remember less than 2, if across this the pH gradient is less than 2, then there won't be any ATP synthesis because the driving force is then too small. So, you are realizing this whole dynamics is all a function of your gradient and flow. As long as you can maintain the gradient, you can always attain a flow. So, I will close in here. Next class we will move on to, now we have an idea about ATP synthesis, we will talk about mitochondria, and we will talk about chemiosmotic hypothesis. Thank you.